This conference will now be recorded.
Yeah, today we'll discuss on uh, evolution of ICs, what IC is and why it is required, and what all you require uh, to develop an IC. Okay, so basically, an IC means it's a integrated circuit that contains several number of transistors fabricated on a single chip. Okay. Uh, how we can classify ICs depending on the size. Okay. See, we have got some five types of ICs. First one is SSI. SSI means it's a small scale integration. Small scale integration means on a chip you can have up to 100 number of or up to 100 electronic components. Electronic components can be anything. It can be transistor, resistor, capacitor, and all. Okay. So if a chip contains less than or up to 100 number of electronic components, then you can call it as SSI. Means range, say it's very less till 100 electronic components. That is called as SSI. Then second one is MSI. MSI means it's a medium scale integration where you can expect the number of electronic components or transistor from 100 to 3000. That is called as MSI, medium scale integration. Next comes LSI. LSI means it's a large scale integration and range again lies between 3000 to 30,000. So next one is VLSI. VLSI means it's a very large scale integration. Then what about range? 30,000 to 10 lakhs. Okay. Then last one is ULSI. ULSI means it's a ultra large scale integration where you can expect more than 10 lakh components lying on a single chip. Okay. That is called as ULSI. Next, what about objectives? Objectives in the sense why you require VLSI. VLSI means, as I told, it's a very large scale integration system, or it's the integration of millions of electronic components within a small area. Okay. Then what about objectives? Objectives, I can say first one, it's speed. The circuit speed is very high compared to the MLSI or SSI. Second one, second objective is power consumption. Power consumption is very less. And third one is, as I said, design area. Means you require a very small area where you can expect more than 10 lakh of electronic components, okay, or fabricated on a single chip. So next one is the next one is VLSI design flow. See, VLSI design flow means I can say how your IC will be designed. Means to design any of the IC. It can be anything. It can be an AND gate IC, NOT gate IC, right? It can be half adder, whatever it is. So what all you require to develop an particular IC. So first step is you should know, means idea, what all the requirement. Say you want to develop one AND gate IC. So AND gate IC means, what is the basic need here? AND gate IC means it has to do the logical multiplication. So that should be the idea. So if you know that, means next step would be specification. What all the specifications you require? Means is it two input AND gate, three input or AND gate, and what else you require? In which language you are writing the code, Verilog code. And when it comes to coding, I can divide HTL description in three ways. First one is data flow description. Second one is behavioral description, and third one is structural description. So what do you mean by data flow description? So in data flow description, what basically we are checking is we are just showing the relationship between inputs and outputs, right? That is mainly done in case of your data flow description. Means how exactly data flows between the register. Okay. So that is explained with respect to data flow description. So next one is behavioral description. So behavioral description means again we are writing the code with respect to the truth table. We are writing the code with respect to the truth table. In the sense, again, take the same two input AND gate, right? For that, how you can show the truth table? Say A and B are inputs, then sum and carry are outputs, correct? Then how many iterations or combinations you can expect here? 4 combinations. As you have two inputs, it starts with 0, 0, 0, 1, 1, 0, 1, 1. Then sum and carry. So with respect to the 4 iterations, we are writing the code. If that is the case, then that particular description you can call it as behavioral description, right? So in data flow, we are just writing the code with respect to the connectivity between inputs and output. In case of behavioral description, you are writing the code with respect to the truth table. Next one is structural description. So in case of structural description, mainly it describes the connectivity between the gates. Getting? So if you are showing the connectivity between the gates, means basically you are explaining the structure of a particular electronic circuit, right? So this description we'll discuss in detail afterwards. Okay. So next is design architecture. Means design means you should know how the flow should be, right? Next part is RTL coding. RTL coding means again you are writing the code either in VHDL or in Verilog, right? So next one is RTL verification. RTL verification means so before converting your code into schematic, you are doing simulation part. Okay. So once simulation part is clear, means with the help of test bench waveform, you are checking the working of your AND gate, say with respect to your truth table. So in test bench waveform, what you are doing is you are setting all the inputs. Say A and B are two inputs, means you can set the inputs like 0, 0, 0, 1, 1, 0, 1, 1. Then you can generate the simulation model. If it is working, if that simulator part is working, means then next part would be your synthesis part. So synthesis part means it's a stage that you are performing after your RTL verification or after your simulation. So in synthesis, what we are doing is we are just converting the HDL code into the schematic or circuit diagram. So once it has been done, then you can go for fabrication part. So foundry, either you can take any workshop or even factory where you can fabricate the IC. So next you can expect the final IC chip. Okay. Okay. Am I audible? Am I audible?
Yes, sir.
Yeah.
Yes, sir.
Okay,
Sir,
fine.
your voice is breaking, sir.
Okay.
Sir, your voice is breaking.
Now check. Okay. So clear? Yeah, now it's audible, right? Is it audible? Okay. So next, where all you can use the IC in case of your microprocessor, microcontroller, memory units, printer, mobile, digital security lock. You can expect these ICs anywhere, starting from calculator, laptop, your cell phone and all. Okay, in all these things you require IC. And what all the specifications you require if you are developing an microphone. Some of you are not muted your microphone. Lingraj, AR, ASP, mute your microphone. Okay, so specifications, first one would be your instruction set, then IO pins, input or output pins. Okay, input pins means you can use within the IC, output pins for the interfacing and all. Next, organization of the system, functionality of each unit in the system and how to communicate to the other units. Next part is design architecture. This is where the main work starts. With the help of the specification sheet, the target IC's architecture is decided and the layout for the same is created by design engineers using EDA tools, electronic design tools. So EDA tools, you can take Synopsys, first one, ActiveHDL, then Xilinx, ISC, Simulator, then Cadence. So these are the different EDA tools. So this is the design analyzer. Means once your simulator part is over, then or once your synthesis part is over, then you can go with this analyzer. So this is the RTL coding, means either VHDL or Verilog code. Again, the RTL coding tools. First one you can use Xilinx, second one VIM, Emacs, Context, and HTL Turbo Writer. Okay. So this is the test bench waveform. I think this we had discussed in the last class, right? So why you require test bench waveform? Means to realize any of the given circuit with the help of any simulator. Since we have started with Xilinx, right? So see what we are doing in case of this test bench waveform is we can set only the inputs here, right? So once you set the inputs, so next part would be your generation of simulator model. Means what it shows exactly, that simulator model will show you the outputs with respect to the inputs that you have set with the help of test bench waveforms, right? So this part is clear, right? Next, again, synthesis. Okay, so synthesis, it's this is where the design now start to get the physical. Okay, logical synthesis is a process by which the desired circuit behaves. Okay. So here, this is your FPGA kit. FPGA means field programmable gate array. So this is your FPGA kit. So what we are doing is we are connecting the PC to this FPGA kit, right? So this is the Spartan kit, and once your simulator part is over, next part is synthesis. So after synthesis, what we are doing is we are connecting your laptop to the FPGA kit, right, through a cable. So next is the same code, whatever you have written in either VHDL or Verilog, in Verilog, that code is dumped onto the kit. Means that after synthesis, that schematic has been developed, right? So that schematic has been dumped onto the FPGA kit. So what happens is this contains n number of gates, right? And say you are checking one 2 input AND gate. So what happens is, out of these n number of gates, only that particular 2 input AND gate has been enabled, right? Then we have a number of LEDs here. Okay, so these are the LEDs, right? Same like your simulator. Here you can set the inputs like 0, 0, 0, 1, 1, 0, 1, 1. And one more thing is you will have control only on the inputs. Okay, and output will be generated with respect to the given inputs. Is that fine? Okay, so foundry means, say once your FPGA if your code is working, or whatever you have designed, if it is working in your FPGA means, then you can go for final part, that is fabrication. Okay, so this is the fabrication part. So next comes the final IC. Applications of VLSI means where exactly you can use this VLSI: in consumer electronics, in wireless domains, in electronic design automation, in medical electronics, in automotive electronics, in aerospace, in defense, in bioelectronics. Okay, in all these areas you can use VLSI. I think last class I had asked you to write one Verilog code for 3 to 8 decoder. Is it correct? 3 to 8 decoder. Have you done that? Have you tried at least 3 to 8 decoder? Anyone? 3 to 8 decoder. So what happens is, in case of 3 to 8 decoder, how many inputs you may require? 3 inputs, say A, B and C. Correct. And what do you require along with these 3 inputs? What else you require apart from these 3 inputs? You require one more input. That is called as what? Any answers?
Enable.
Yeah, fine. Enable is one more input, right? That basically controls your working of decoder. So if enable is high means it won't check for any of the 3 inputs A, B or C. Irrespective of these 3 inputs, it will be giving you the output as what? All zeros. Correct, right? If enable is low or 0, next what it does? If enable is 0 means then only it checks your input. If it is 000 means, I think D0 will be high, other bits they'll remain 0. Correct, right? Then if the inputs are 001 and enable is 0, then D1 will glow, other 7 outputs will remain 0. Correct, right? Then last iteration, if enable is 0, if inputs are 111, then D7 will be high. Then other 7 outputs they'll remain 0. Next we'll check one more program here. Up to this clear, right? Any doubts here? Any doubts?
No, sir.
Yeah, fine. Yeah, we have one more program. These programs basically we are checking in labs. Okay, so 8 to 3 encoder without priority. right? So for this, this is the RTL schematic. Means how many inputs it may require? 8 to 3 encoder means 8 is input, 3 is output, and you require one more input called enable, right? So if enable is high, again it won't check for any of the 8 inputs. Is it correct? So including enable, I can say it has got 8 plus 1, 9 inputs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 inputs and 3 outputs. So if enable is 1 means it will not check for any of the inputs. CZ means I can say it's high impedance, right? Or you will not get the appropriate output. Then if enable is 0, if enable is 0 and you made only D7 bit as high, next what will happen? See, he has shown like this. See, this is, don't get confused, this is your LSB, getting, this is LSB and this is your MSB, getting my point? If D naught is high, then you can expect all the 3 outputs as 0 0 0. Am I correct? If D naught is high and remaining 7 inputs are 0, then you can expect all the outputs as low. The next iteration again enable is 0, right? Then this time you made D1 as high. Okay, means I'm just increasing the weights here. Now I have increased weight by 1, means I made D1 as high and other input bits as low. Then I can expect only D3 will be high. Okay, then for the last one, means if you make D7 as high means you can expect all the outputs as high. Fine. So this is about 8 to 3 encoder without priority. So this is the code here. And one more thing I would like to clear is this code is written in Verilog. Fine. So module name is WPN code. Within that you are passing all the inputs and outputs. Enable, DIN and DOUT. DIN is the input that can take 0 to 7, means 8 bits. Then DOUT can hold only 3 bits because it's a 8 to 3 encoder without priority. Again I am declaring here, and this is register, and this is the keyword, always at the rate inputs, means within this always you need to pass all the inputs, enable as well as DIN. Okay, then begin. So what it is, see, your syntax of your Verilog code is same as that of your C language. Okay, if enable is 1 means it will not give you the proper output, correct? If enable is 1, then DOUT equal to 3 dash. 3 dash means it can hold 3 bits at a time. So high impedance, or say it's inappropriate output. So if enable is 1, you will not get proper output. Else means you are making enable as 0. Then your then your encoder will act with respect to the truth table, with respect to this truth table. If enable is 0, then it will check for the given inputs, right? So if enable is 0 and DIN is high or D naught is high, then you can expect all the outputs as 0 0 0. Then see, you are within the, you are into this loop. Okay, then A dash B after D naught, D of 0, say D of 1 is 1. For this you are getting output as 0 0 1. Then for B of 2 you are getting output as 0 1 0. Then for the last iteration, right, you are getting output as 1 1 1. When you can expect the output as 1 1 1 if you are making MSB of your input as high. Okay. Then end case means you are closing this case, and here within the case you are not passing any enable. Why you are not passing enable input here? Because it has already decided if enable is 1, right, output will not be proper. Else means it will assume that enable is made as 0, right? So we are not passing any of the enable input within the case, and I am passing only the DIN input. Okay, DIN not DIN 1, DIN 2 till DIN 7. End case, end means I am closing this part. One more end means I am closing this part. End module means I am closing the module. So clear? Okay, so next one is 8 to 3 encoder with priority. With priority means it will give the priority for the MSB bit. Okay. He has shown this with respect to enable as high, means active high enable. So in this case, what happens is with priority encoder means, see, if you want, even you can revert this, means you can make enable as, say you are checking with respect to active low enable. Then, so first iteration you can show enable as high. Again, it will not check for any of the inputs. It will give you the output as ZZZ. So next, you make this enable as 0, right? If enable is again 0 means, see, if you want you can change. Otherwise, we will check with respect to the same truth table. Means here we are checking the truth table with respect to active high enable. Okay. Now see, enable is 1. It will check for, you set it for D7 as 1. If D7 is 1 means it will be giving you the output as 1 1 1. Okay. Then next priority. See, highest priority is being given to D7, right? If D7 is high means it will not check for D6. Don't care. See, getting right? See, what happens is in case of priority encoder, if MSB is high, it will not check for the lower priority bits D6 to D0. It won't check. If D7 is high means, right, by default it will give you the output as 1 1 1. So this is the highest priority we have set for D7. Next, say D6 is high. See, if D6 is high means it will give you the output as 1 1 0. But remember, we have made D7 as 0 here, right? See, correct, right? D7 is highest priority. Then D6 it will come down priority. Then D5, D4, D3. Say I have made both D7 and D6 as high. I have made both D7 and D6 as high. Means what it has to produce output? It will produce you the output as 111. Means if D7 is high means your D6 can be anything. It can be 0 or 1. So if D7 is 1 means it has to produce, or it will produce output as 111. Getting right? Next, D5 is 1. D5 is 1 means output is 101, right? Then last priority, D0 is high. D0 is high means it will produce output as 000. So any doubts here? Any doubts? Hope it is clear. Clear, right? If D7 and D6 both are high means it will consider highest priority bit as D7. With respect to D7, it will produce the output as 111. Okay. So Verilog code for the 8 to 3 priority encoder module priori. You can give anything followed by enable, din and dout. So we are passing all the inputs and outputs here. Then input is enable. Then input, what is the range here for din? It is 0 to 7. Then output 0 to 2 because it's a 8-bit. Sorry, it's a 8 to 3 priority encoder. So output will hold 3 bits at a time. Then register dout. So this part we are using only in case of Verilog. Okay. Pi that we will discuss later. Then always. So see, if you are using always in your Verilog code means it indicates it's a behavioral description. Getting? If you are using always, right, in your Verilog code means it's a behavioral description. Then begin if enable equal to 1. So as I said, on the truth table will show you the active high enable. If you want, you can make it as active low also. If enable is 1, right, then what it will produce 3-B-ZZZ means you will not get the proper output. If enable is 0, then it starts giving you the outputs priority wise. Clear? Clear? Any doubts here? So you can check core here. So once you declare always, and within always say you're shown both enable and din. So next part you need to pass the din within the case X. Okay. So say 8-B0000 next 1. Okay. So this is your D naught, right? If it is 1, it will give 000. Clear? Say this is the highest priority. Your D7 is or din is, or say it's a din of 7. If it is 1 means it will not check for any other lower priority bits. Don't care. Directly it will give you the output as 111. Suppose say I have made 8-B11 remaining inputs as XXX. Then again it will give you the output as 111 only. Because if MSB or if D7 is high means it will not check for D6 or D5. They may be zeros or ones. It will produce you the output as 111. Clear? So any doubts here? Any doubts? Any doubts?
No, sir.
Okay. So today we have discussed about the evolution of integrated circuit. Okay. Followed by the actual process, means how exactly you can design an IC and all. Okay. Right. So any other doubts? Any other doubts? Abhinandan, any doubts?
No, sir.
Okay.
No doubts.
Yeah. Thank you. Thank you for joining.
Sir,
Thank you, sir.
hello.
Yeah.
Sir, will you send the notes, please?
Sorry.
Notes, sir, this PDF.
1 minute.